Hi everybody, so we're moving into chapter 6. We're talking about the normal distribution. So this is the primary distribution that we're going to be using throughout statistics. This is our bell-shaped curve that we've talked about a little bit so far. But the normal distribution, so we describe it using a capital N, and we look at primarily the mean and the standard deviation of this normal distribution. So, like I mentioned, it's that symmetric bell-shaped curve, right? There's the bell curve. So we're going to be looking at the mean, the middle value, and then the standard deviations we've seen with the empirical rule tell us how far away from that middle, that mean, we are. So if we look at the center of the normal distribution, this is the highest point, okay? It's the peak of the curve, and this divides up the area into two equal parts. So we have, this is the mean, median, and mode. This is our middle, divvying up the values into the lower 50% and the upper 50%. So when we're looking at the spread of the normal distribution, that depends on both what the mean is and also what the standard deviation is. So the larger the standard deviation, the more spread out the data is, the smaller the curve is going to be. So you can see on our couple examples here, right, standard deviation of 2.5, very thin, tight curve, but if you go all the way to standard deviation of 7, very long, drawn out, and low curve, because everything is much more spread out when the standard deviation is higher. Okay. So here, in section 6.1, we're going to talk about the standard normal distribution. So the standard normal distribution, this incorporates our z-score. So we've talked a little bit about the z-score back in a previous chapter, but here's where it can really start to come into play. The standard normal distribution allows us to look at really any data we want to, and it normalizes it. It standardizes that data so that we can look at it all basically on the same scale. So suppose that a random variable x is normally distributed with mean mu and standard deviation sigma. Then the random variable z is equal to x minus mu over sigma. So this is the normally distributed curve with a mean of 0 and a standard deviation of 1. This is very important because now, regardless of what the data was, regardless of how big, how small it was, if we can standardize a normal random variable, this allows us to work with the data using the same numbers every time on this scale with a mean of 0 and a standard deviation of 1 every time. Okay? So, for example, what is the z-score of x? When x equals 1 and our random variable is defined using a normal curve with a mean of 12, standard deviation of 3. Right, so that's our mean and that's our standard deviation. So this would be z equals 1 minus 12 over 3. Right, x minus the mean over the standard deviation, so that's negative 11 over 3, and rounded as a decimal, negative 3.67. And this can tell us how far away this data point is from the mean. In this case, it is almost 4 standard deviations away from the mean, which, if you remember your empirical rule, is actually really far away. So in this example, Jerome averages 16 points in a competitive sports game with a standard deviation of 4 points. So it's normally distributed, mean of 16, standard deviation of 4, so that's this right here. Suppose Jerome scores 10 points in one game where the z-score is negative 1.5 when x equals 10. Interpret this result with respect to the mean and in the context of his competitive sport game. So what this means in terms of the mean, and in the context of the problem. So that negative 1.5, that tells us that this score was 1.5, so 1.5 standard deviations below the mean. So this score is below average. Okay, and if we look at how significantly below average this is, it's fairly below average, right? So 1.5 standard deviations. So if it's within 1 standard deviation, we'd say, well, that's pretty close. That's fairly expected. But with a value that's greater than 1 and getting even closer to 2, we can say that this is, I would say, somewhat significant in terms of how low this score is compared to the mean. So here are some properties of the normal curve. So a few things to take note of here. This curve has inflection points. This is where the graph changes curvature at 1 standard deviation from the mean. The total area under the curve is equal to 1. So this one is going to be really important when it comes to calculating a lot of the values that we're looking for. The area under the curve to the left of the mean is equal to the area under the curve to the right of the mean, right? Because it's 50% and 50%, right? So it's 0.5 and 0.5, right? So each of those is 0.5. The graph tails off towards the horizontal axis on the left and right, and then, of course, the empirical rule holds for this one. So just as a reminder what the empirical rule says, it says that as long as we are within 1 standard deviation of the mean, so here's the mean right here, right in the middle. If we're within 1 standard deviation, 68% of our data lies within 1 standard deviation. Okay? And then if we move out even just one further, so we move out to 2 standard deviations from the mean, now we have 95% of our data lying within 2 standard deviations of the mean. And then as far out as we are going to go here, that's 3 standard deviations away from the mean. That means 99.7% approximately of our data lies within 3 standard deviations. And so there's this tiny little portion out here in the tails that we can encounter occasionally. But this is what the empirical rule tells us. So one thing the empirical rule helps us do is it helps us break down this data and look at it proportionally. So notice that because 68% of the data lies within 1 standard deviation, so again this is 1 standard deviation right here, we can split that up, right, to below and above the mean. So that tells me that this is 34 and that's 34, right? It's half of 68. This portion is 13.5, that's 13.5. 2.35, 2.35, and then in the tails is a 0.15%. So very small portions as we head out there towards the ends, but this is going to be very helpful for us when we are trying to identify portions of data, where all the data lies. Okay, so let's look at an example that we've already looked at a little bit. So using the standard deviation and mean and assuming normal distribution, find the prices of peanut butter that lie within 1, 2, and 3 standard deviations from the mean. So, and interpret your answers in the context of the empirical rule. So we're looking for all of the data that lies within 1 standard deviation, within 2 standard deviations, and within 3 standard deviations. Okay, so the mean, we saw here the mean is 3.68, and standard deviation is 0.26. So that means any data point that lies within 26 cents of this number is within 1 standard deviation. And it looks like 3 of those values are within 26 cents. of 368. So those numbers in ascending order would be 359, 375, and 379. Those all lie within 1 standard deviation of that mean. Now within 2 standard deviations, we have all the same ones, so same as above, and also the other 2 data points. So 329 and 399 also both lie within 2 standard deviations of the mean. And then within 3 standard deviations, well, if all of these were within 2 standard deviations, of course they must also be within 3. So all above are within. And if we compare this to what the empirical rule tells us, so notice here, within 1 standard deviation, we have 3 out of our 5 data points. So 3 out of 5, that is 60% of the data. And that is, I would say, fairly close to 68%, right, given the context of 100%. So we get 60% within 1 standard deviation, and now once we reach within 2 standard deviations, that includes all 100% of the data. And so we're told by the empirical rule to expect it to be around 95%, and that's around 95%, right? We just have a very small sample size here. So there's 100%, and then of course still 100% of the data is within 3 standard deviations as well. All right. So the Acme company manufactures widgets. The distribution of widget weights is bell-shaped. The widget weights have a mean of 51 ounces and a standard deviation of 4 ounces. Use the empirical rule to answer the following questions. So 99.7 of the widget weights lie between what 2 weights? All right. So in order for us to determine 99.7%, so if we have a normal curve over here, here's our mean, and then we go out 1, 2, 3, and 1, 2, 3. 99.7% of the data, according to the empirical rule, is going to lie within 3 standard deviations. So that's going to be from here to here. It's going to be everything in here. Okay, so we want all of the data points that lie within this region. So if the mean is 51, so the mean is 51, and the standard deviation is 4, so that means every standard deviation we move up or down, we're going by 4 units. So we're going up 1, 2, 3 standard deviations up, and 3 standard deviations down. So we're going to have 51 plus 3 standard deviations, which are 4 ounces each. So that becomes 51 plus 12, which is 63. And then 51 ounces minus 3 standard deviations that are 4 ounces each. So 51 minus 12, and that's going to be 39. So 99.7% of the widget weights lie between 63, or excuse me, let me start with the lower one, lie between 39 and 63 ounces. Okay. Now, what percentage of the widget weights lie between 43 and 63 ounces? So for this one, we will also go ahead and construct a normal curve here. and we put our mean on here. There's 51. Now if we actually look at the standard deviations, what their values are, as we go up 4 or down 4 each time. Let's see, this one is 55, this one's 59, oops. This one's 63. This one going down 4. That's going to be 47, that's 43, and that is 39. Okay. So we want the percentage that lies between 43, so right here, and 63, right here. So that's going to be everything in here. And we can get this information again from the empirical rule. So the empirical rule tells us that from here to here, so this distance right here, that's 2 standard deviations to either side. So that means that this whole region between the red bars, so from here to here, that is going to be 95% of the data. And then all that's left is this little piece right out here. And that, if we just go back up here, that little piece is going to be 2.35% just by itself. So that's going to be 2.35%. So we just take 95 plus 2.35. That's 97.35%. So that's what percent of the weights we expect to lie between those two values. And then what percentage of widget weights lie above 47? Well, we do the same kind of thing, get our normal curve. But here we really only care about the value of 47. So here's the mean. There's our 51, and then we're down 1 standard deviation, that's 47 right there. And we only care about everything above 47. So we know that everything from 47 to 51, this portion we saw in that graph up on top, that's going to be 34% of the data. And then from here onward, so this whole portion here, that is half of the area, right? Because it's symmetric, so that's going to be 50% of the total area. So we have 34 plus 50, and that's 84% of those weights should lie above 47 ounces. All right, and that is section 6.1. So now, when we're looking at using the normal distribution, so we're going to look at what we can actually use it for, start making some interpretations here about this. We're also going to be incorporating the technology here a bit, so you want to get your Desmos handy if you have it. So when we're looking at a normal distribution, a normal curve, we're going to be interpreting that area beneath the curve as either a proportion or a probability. So if we ignore this example, looking for area under a normal curve. Suppose that a random variable is normally distributed. The area under the normal curve for any interval of values of the random variable x is either the proportion of the population with the characteristics described by the interval of values, or the probability that a randomly selected individual from the population will have the characteristic described by the interval values. So in other words, if we say that the area under the curve represents a proportion, we say, okay, well, the value we got is, 0.5. Then that would say, well, the proportion of the population that this applies to would be 50%. Or we can look at it and say, okay, well, we got 0.5. Well, then that means that the probability that any randomly selected person in this group has this condition would be 0.5, right? A 50% chance. So let's look at an example of this to help us with our interpretation here. So the weights of giraffes are approximately normally distributed with mean 2,200 pounds and standard deviation of 200 pounds. So first off, draw a normal curve with the parameters labeled, then shade the area under the normal curve to the left of x equals 2,100 pounds. So let's go ahead and do that. So I'm going to space it out, give me some extra room to write. And I try to make it as bell-shaped as I can. Okay, so our mean is going to be right there in the middle. We're going to be out 1, 2, 3 standard deviations on either side. Okay. So the mean value, that's going to be right here in the middle, so that's 2,200. And then our standard deviation is 200. So that means every time we move up or down one of these bars, we're moving up or down by 200 units. So 2,200 plus 200, that's 2,400. Plus another 200, that's 2,600. Another 200, that's 2,800. If we go down now, 2,200 minus 200 is 2,000. Then 1,800. Then 1,600. So now it wants us to shade the area under the normal curve to the left of 2,100 pounds. So 2,100 pounds, that's going to be right here in between 2,000 and 2,200. Okay, so that's going to be 2,100 right there in the middle. And then we want to shade the area to the left of that. So that's going to be everything over here. Right. Now, for part B, it's asking us, suppose that the area under the normal curve to the left of 2,100 pounds is 0.3085. Provide two interpretations of this result. So when we're interpreting our results here, we can talk about this as a proportion or as a probability. Okay, so let's start talking about it as a proportion first. So the 2,100, that's a weight, right? And the 0.3085, we're interpreting that as a proportion or a percentage. So we can say the proportion of giraffes that weigh, now notice we're using all the values less than, right, to the left of 2,100. The proportion of giraffes that weigh less than 2,100 pounds is 30.85%. Wherever my percentage key is. I think I'm going crazy. I don't see a percentage key. Oh, wait, there it is. There we go. So the proportion of giraffes that weigh less than 2,100 pounds is 30.85%. Now, as a probability, we say the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085. Okay, so when we are talking probabilities, then the value always has to be between 0 and 1. So we can say, as a proportion, the proportion of giraffes in this population that weigh less than 2,100 pounds is about 30%. Or, as a probability, we say the probability that just any random giraffe that I select, the probability that it weighs less than 2,100 pounds is 0.3085. All right. Next up, standardizing a normal random variable. So we've already talked about this in the last section, right? This is the z-score. So being able to take data that, like in this last example, can get kind of large, can get kind of hard to work with, we can standardize it so that it has a mean of 0, a standard deviation of 1, and then we can work with it a lot more easily. This is also going to be helpful on a technological aspect because we can work with the standard normal curve then in all cases. We don't have to worry about trying to find that curve somewhere on these high values. Now, finding the z-score, if we were doing this manually, so if we were doing this in class, we would use the z-score table to do this. And we would have a lot of discussion on the use of the z-score table, how to read it. But since we are doing this using the technology, we're going to be using Desmos primarily. We will go through how to actually do this on Desmos as we start going through examples here. So let's take a look at an example. So IQ scores can be modeled by a normal distribution with mean of 100, standard deviation of 15. Round to 4 decimal places for these values. So find z when an individual's IQ score is 120. So we're looking for the z-score when the individual's IQ is 120. So that's going to be x, right? So the value minus the mean, so 120 minus 100, over the standard deviation. So that is going to be 20 over 15, right, or 4/3, but that's also, as a decimal, 1.3333, right, rounding to 4 decimal places. So we get 1.3333. On the normal curve, so on the original curve, we would plot, right, the mean here in the middle, so that would be a mean of 100, and it's going up 15 every time. So that's 115, that's 130, etc. And the value in question would be, so 120, that's going to be right in here. Right, so that's 120. But instead of working with those numbers, we can instead work with the standard normal curve, which puts this at 0, standard deviation of 1. So we're just counting up by ones the whole way. So our value of 1.3333, it's in the same place, so it's right here, it's about 1 1/3. Okay, so that's 1.33 right there. And what this example is asking us for is the area under the standard normal curve to the left of that z-score. Okay, so we're looking for, remember we interpret this area as a probability, so we're going to write this as the probability that z is less than 1.33. Go ahead and just round it to 2 for this one. So this is the probability that we're looking for. Now, when we want to compute this using the technology, so using Desmos in particular, so we're going to switch over to Desmos. Now, Desmos does have statistics functions, so if we go over to distribution, you'll notice there's a button here, normal distribution. So you can just click that. or you can type it in, right? Just type in normal dist. Okay? And then notice if you don't do anything different, Desmos assumes that it's the standard normal. It has a mean of 0, standard deviation of 1. You can see that up in the corner. Now, if we wanted to change that, we could input the mean and standard deviation manually. So if we wanted to use our specific data, so mean of 100, standard deviation of 15, we could do that, and then that's going to move the curve over here. I zoomed out too much, it's very hard to see. So you can see this isn't particularly helpful because now you can't even see the curve anymore, right? In order to see that it's so flat, because the standard deviation is 15, so that means one standard deviation is right there, between 85 and 115. That would be one standard deviation. Not very helpful. So if we go back, and let's get rid of these extra parameters. So we'll just go with the standard. 0 mean, standard deviation of 1. Okay, so there's our normal curve. The nice thing that Desmos can do for us is if you click Find Cumulative Probability, so CDF, right there, Desmos will give you the area under the curve. So if you don't specify anything, it'll just assume that you want the whole area, and that's 1. Now, for our purposes, we want everything less than 1.33, which is 0.9082. Okay, round to 4 decimal places, so 0.9082. So 0.9082. That would be the area under the standard normal curve, less than 1.33. Now, if we interpret this in the context of IQ scores, well, we interpret this similarly to how we did the last one as well. So we say the proportion of people with IQs below 120 is 90.82%. Which would hopefully make some sense, because when we're looking at such a high IQ, it makes sense that most people would have an IQ below 120. And then, of course, our interpretation is a probability. We say the probability that a randomly selected individual has an IQ of less than 120 is 0.9082. So that's what we get out of that statement. And then for this last part here, use the complement rule to find the area to the right of z. So if we're dealing with our z-score here of 1.33, that's right there, 1.33. Now we want everything to the right here. Now, using Desmos, that wouldn't be too challenging, but we can use the complement rule for this. So the probability that z is greater than 1.33 equals 1 minus the probability that z is less than 1.33. Right, so since we know that everything below 1.33 and everything above 1.33, that's 100% of the data. So if 90% of the data was below, 10% is going to be above. So that's going to be 1 minus 0.9082, which is 0.0918. And of course, if we wanted Desmos to take a look at this for us, we could do that as well. So instead of making the maximum value 1.33, we make the minimum value 1.33. Notice Desmos is taking that area above, and we have 0.09175, right? So rounds to 0.0918, which is exactly what we got before. So here it gives you steps for finding the value of a normal random variable. So this is basically what we were just talking about. So we're interpreting as proportion or probability, and then we're looking at the standard normal curve, and then getting the corresponding z-value that goes along with that percentage. Now, in this example, we're looking at kind of the reverse of what we just did. So in this case, instead of saying here's my z-score, what portion of the data lies above or below, I'm telling you here's the portion of the data we're looking at. Now you tell me what the z-score is that corresponds to that value. Okay, so the combined score on the GRE is normally distributed with mean 1049 and standard deviation 189. What is the score of a student whose percentile rank is at the 85th percentile? So the 85th percentile. So what does that mean, the 85th percentile? Well, it means that you scored better than 85% of everybody else that took it. So that means the student who scored in the 85th percentile is going to be somewhere up here. And that means all this data down here is going to add up to 85%, so to 0.85. Okay, so that's 0.85 right in there. So now, what we need to do is find this value, which I'm going to call z0. Find what that value is so that the probability that z is less than z0 is 0.85. Alright, so we need to find that value. Find that z-score that gives us 85% below it. So to do this on Desmos, so if we were using a table, we would know how to read the table this way, but using Desmos, there is a function that allows us to do this. So if we go back to our normal distribution, let me turn off the cumulative probability. What you're going to do is you type normal distribution 0, 1, and then you're going to put a period, and then you're going to put, so you can either just come in here, so you'll see inverse CDF right here, put that in, and then you're going to put whatever percentage it is that lies to the left of your data point. So in this case we're looking for 0.85, and this number that it gives us, that is going to be the z-score. So you take normal distribution and then dot inverse CDF, put in whatever proportion of your area you want, less than that number, and we get, in this case, 1.036. So we get 1.036. So that's our 1.036. Now, this is not the answer yet because we're looking for the score of a student. And 1.036 is the z-score, it's not the test score. So, right, or the exam score. So we know to get the z-score, we would take, right, x minus the mean, 1,049 over the standard deviation of 189. And normally, we would plug in the value of x right here. However, we don't know the value of x this time. What we do know the value of is z, or z naught in this case. So we know that this is equal to 1.036. So if we want to now solve for x, so what you're going to do, right, you just do some algebra on this, multiply the 189 across, and then add the 1,049 over. This is going to give you the student's score, which is 1244.804 technically. Right? But really we're looking 1244 approximately. So a student who scored 1244 on the GRE is in the 85th percentile, right? Or scored better than 85% of everybody else who took that exam. Okay. Let's look at one more. So it is known that the length of a certain steel rod is normally distributed with a mean of 100 centimeters and a standard deviation of 0.45 centimeters. Suppose the manufacturer wants to accept 90% of all rods manufactured. Determine the length of rods that make up the middle 90% of all steel rods manufactured, and then we'll round to 2 decimal places if need be. So we want to figure out where the middle 90% is of all of this data. So we're going to get the middle right there. So this whole portion inside, that's our middle 90%. So as a decimal, this is 0.90. Which means out here in these tails, this is going to be important. The tails aren't 10%, right? Because there's 2 of them. We're splitting this into 2 pieces. So this one has 5% over here, 0.05. And this one also has 5%, so 0.05 for that one as well. So when we're trying to identify what lengths of rods we want the middle 90% to be between, we need to figure out this z-score, I'm going to call it z1, and this z-score, which I'm going to call z2. So when we're reading this, so we always write probability z less than the z-score we're looking at, and probability z less than z2. And we're always looking to the left. So the amount of area below Z1 is just 5%, so that's 0.05. The amount of area below Z2, and you got to be careful here, it is 90%, but it's also plus that additional 5. So that's going to be 0.95 area below Z2. Now when we compute this, so we're going to go into Desmos here, and we're going to find these values. And we're going to do the same thing we did before. Standard normal curve, because that works out nicely, just like it did on the last one. So standard normal curve, area to the left of the first one was 0.05. So the z-score is negative 1.64 if we round to 2 decimal places. So that's negative 1.64. And then the other one, if we have 95% of the data below it, that's positive 1.64. So hopefully that's not too surprising that these values are the same, but just opposites, because it's symmetric, right? So it makes sense that they would be symmetric across 0. So to find the actual lengths of the rods, we just do the same thing we did last time. So we say Z1 equals, call it X1 minus the mean of 100 over standard deviation of 0.45 equals negative 1.64, and z2, it's going to be x2 minus 100 over 0.45 equals positive 1.64. So do the algebra on this. We get x1 is, oops, excuse me, not 0. We get x1 is 99.262, and x2 is 100.738. Okay, and so we can round this to 2 decimal places, so 99.26 and 100.74. So, but then the answer, because it's asking us where the middle 50%, or excuse me, middle 90% of these rods are, and we can say that the middle 90% of rods are between 99.26 centimeters and 100.74 centimeters. Okay. So if the manufacturer only wants to accept the middle 90%, right, they want to get rid of any values that lie outside of that because maybe they're not up to the specs they need, they would reject anything that's outside of that, so lower than 99.26 or longer than 100.74. And then the last thing here, when we're looking at a bit of notation here, the notation z sub alpha. Z sub alpha is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. So we typically, as you've seen in these last examples, we like working to the left when we're talking about area under the curve, but the alpha value, and we'll see this come up in future cases as well, z sub alpha is the z-score, so it would be z sub alpha is whatever z-score it takes so that this area to the right is alpha. Okay, whatever that may be, right? It might be usually it's a pretty small value, right? Less than 0.05, less than 5%. But we'll talk more about what alpha exactly means in future sections. Okay, so that brings us to the end of Chapter 6. So that's kind of the